The first type of integral that we are going to talk about in this chapter is called the line integral. And to kind of motivate what we're wanting to do with this, let's look back at all the different types of integrals that we have discussed so far. So back in Calc 1, we were able to take the integral of a function of one variable over some interval. And we interpreted this back then as an area. In this class, we've discussed double integrals and triple integrals. I'm just going to write a double integral. So we have the double integral of some function of two variables over some region in the plane. And we interpret that as a volume. Of course, when we got to triple integrals, that was a little bit trickier to do. We didn't want to talk about fourth dimensional volumes. So we kind of lost our geometrical interpretation of it. And in fact, the geometrical interpretation might actually be a little bit of a handicap for what's kind of going on here. What we're really doing is we're taking the function and we're adding up values of the function. For our original Calc 1 integral, we've got this function. It's defined over some interval in the real line, going from A to B, and it has a whole bunch of different values. And we want to add up all of those values. Basically, the total value of the function over that whole interval. Of course, we can't just add all of them up. That's infinitely many points. So that's why we do the integration. Why we essentially multiply the values of the function by little pieces, little line segments on our interval, and that allows us to essentially add up infinitely many things and get a finite number. Same kind of thing for our double integral. So we have our region D. We have a whole bunch of different values of the function in that region, and instead of just adding them all up and getting infinity, we multiply them by the area of some box around our sample points, and that area shrinks to 0, making sure that everything comes out to be finite. So really an integral is a sum. We're adding up a bunch of values of a function. And that's the actual idea that we want to take away from that. And that's going to help us when we get to line integrals. Essentially, we're going to do the same kind of thing where we look at a function of two variables, so an f of x, y, but instead of adding up everything over some region D, some area D, we'll look at some curve. We'll call this curve C. We can essentially treat this as our integral over a function of one variable, but kind of done over this curve instead of a straight line along the x-axis. We would write this as something the integral over the curve C of our function, f of x, y, and we'll put ds. S here is usually used for arc length, sort of like how we have A here standing in for area. So essentially what we're trying to do here is add up the values of the function along some curve. Now I've drawn this in 2 dimensions. We can also do this in 3 dimensions, and the idea is going to stay the same. But how do we actually accomplish that? Well, first of all, let's actually define our curve C. Usually we'll do this using parametric equations. We could do something like x equals some function of t. I'm not going to change this to anything other than the name of the variable. We won't be using other function names other than x, y, and if we're working in 3 dimensions, z. So a curve in 2 dimensions could be written in parametric equations. In 3 dimensions, we have a third equation. Or we can also write this as a vector valued function. So some r of t, which has components of x and y. Or if we're working in 3 dimensions, we also have a z. These are just kind of two different ways of writing the same curve. I'm going to actually draw my curves in 2 dimensions just to make it a little easier to work with. But let's say we have some curve C. It looks something like this. It has some starting point and some ending point. Usually we'll be given some range of t values that we put in here. So maybe this is r of a, meaning that I plugged a into here and got this point all the way to r of b. I want to break up C into a bunch of little pieces. So we have all these little pieces of our curve. Actually, what we've done here is we've picked a bunch of different t values, and these are r of those different t values. So we could say, actually, should be a less than t1, t2, all the way until we get to b. So a bunch of different t values, and we get the different points on our curve. For a particular piece, we'll call the length of that piece delta s. I'll just use I here. We'll say it's the ith piece of our curve. That's the arc length of that piece. On that piece, we'll also take some sample point. So it'd be something like xi star, yi star, or if we're working in 3 dimensions, of course, we'd have a zi star in there as well. And once we've done that, we can take that sample point, plug it into our function, multiply it by the arc length, and add them all up, and take the limit. So we made a Riemann sum here, and by taking that limit, we get what we call the line integral of f along this curve. Now that's the formula for 2 dimensions. For 3 dimensions, all we end up doing is we have the zi star in here, and we have the z over here. Same formula, still given by a Riemann sum, and the same idea about how we actually form that Riemann sum. Now, of course, as always, we don't want to have to use the Riemann sum to evaluate these line integrals. So we're going to think back to chapter 10 when we talked about the arc length of a parametric curve. Remember there, we derived a formula that the length of a parametric curve is given as the integral from a to b, where a and b are the same a and b that we did here. We took the square root of the derivative of our x parameter with respect to t squared. And same thing with the y. Later I think it was in chapter 12, we also then extended that to 3 dimensions. We'd end up with an extra dz dt squared integrated with respect to t. Now, essentially, all we really did here is we derived an approximation for our arc length, our delta si's, in terms of the distance formula, or you could say the Pythagorean theorem. And that's where all this came from. Essentially, their delta s was being approximated. Maybe I should write this as an approximation, as a square root of the approximate value, the differences, the small differences in x and y's. So if we're kind of estimating this arc length by just the straight line from this point to that point, we have our difference in x squared plus our difference in y squared and the square root of that. But then we want to have everything in terms of t, so we would end up pulling out a dt. But by pulling out a dt, we end up having to divide by dt inside. So we end up with a delta x over delta t squared plus delta y over delta t squared with a delta t on the outside. And then as we take our limit, this approximation gets even better, and these difference in x's over difference in t's and difference in y's over differences in t's, those turn into the derivatives. with the obvious modification for three-dimensional space. But what that essentially means is that we have some fairly nice formulas for actually doing the line integral. In 2 dimensions, we can take our line integral of this function over a curve C by plugging in the values, the parametric equations for x and y in terms of t, and then multiplying by this square root, the same square root that we use to actually do arc length. In 3 dimensions, we do exactly the same kind of thing. We plug in our parametric equations for x, y, and z, and then we multiply by the square root of all the derivatives squared. Of course, we can also even simplify this, or not really simplify it, but rewrite this in a simpler looking form by using vector valued functions. Both of these can be rewritten in this form over here. Essentially, we're plugging in r of t. R of t is, remember, is just the x, y, z, or x. If we're working in 2 dimensions, it's x and y. By plugging it into f, we're essentially just plugging in x, y, or x, y, z into their corresponding spots. The magnitude of r prime, remember, the derivative r is just the derivatives. So r prime of t is dx dt I plus dy dt j, and in 3 dimensions, dz dt k. And then the magnitude of this is the square root. Take those, square them, add them all up, and then take the square root. So these are really just 2 different versions of the same formula. Now, of course, being able to do what we just did require us to have derivatives of x, y, and z. If we can't differentiate those functions, things are not going to work out. So that's the formula. Those are the formulas that we're going to use when our curve is smooth. Remember, smooth means that the derivatives exist, and technically also means that the magnitude is never 0. We won't really worry about that too much. But the point here is, if we want to integrate over some curve like that, we'd be fine. Everything here is very nice and smooth. If we wanted to instead have some corner in there, things are going to be kind of an issue. So we're going to talk about what we call piecewise smooth. And this is not a very complicated concept. Essentially, a piecewise smooth curve is one that is made up of finitely many smooth curves. So we could have something like, well, let me make it a little bit smaller. So we have something that is nice and smooth here, but then kind of takes a corner. Maybe it has another corner. But it's just made up of different pieces. So this whole thing might be called this curve C, but then we have a C1, a C2, C3, C4, where each of these C's is a smooth curve. And then if we do that, then the line integral of some function, I'm just going to write it little f instead of f of xy or f of xyz, because it's going to be the same formula regardless of dimension. But we can just essentially do the integral over each piece separately and add the results together. And so on and so forth. It doesn't matter how many there are, as long as there's finitely many pieces. If there's infinitely many pieces, things can get a little off, and you don't really want to deal with that here. Being able to actually split up a line integral this way is actually going to be pretty important when we get to Green's theorem in section 16.4. And Green's theorem is one of those big theorems that we're mostly concerned about. So we want to make sure that we can do this. But really, there's not much more to say about it. It's kind of how we already knew how to split up integrals back in Calc 1 when our functions were not necessarily good on every piece all at once. We couldn't use the same formula for every piece. We might have to split it up into multiple integrals. This is really just the same kind of thing. So let's actually just jump right into a problem. We have this function, we have the function x, y to the fourth power. We want to integrate over the curve. They didn't actually give us a parameterized curve here. They described the curve to us. We're going to have to come up with a parameterization of the curve. Of course, it is just a circle. For circles, one easy parameterization is to use trigonometry. Essentially, we set x equal to something cosine, let's just do theta, and y equals sine theta. Of course, cosine and sine are really good for the unit circle. This is not the unit circle. It is centered at the origin, but it has a radius of 4. So we end up having to multiply our trig functions by 4. Let's go ahead and actually plot this circle. So our curve here was the circle. X squared plus y squared equals 16. Let me get rid of the label there. So we've got a circle of radius 4. Of course, we're only really looking at the right half of this circle. So how do we get this right half over here? Go ahead and make a curve. Remember, we put in cosine, 4 times cosine. I'll use t here instead of theta. Our parameter is t. And we're really looking at what parameter values do we want to take? Well, on our unit circle, and this is really just the same angles here as the unit circle, we'd have 0 here, pi over 2 here, but if we want to go from here all the way around to here, we have to go back to negative pi over 2. So we go from negative pi over 2 to pi over 2. Now, of course, you can't really tell that there's only the right side of the circle because I got the other circle there. If I take that out, we can see that this curve actually does just give me the right half of the circle. And that's what we want to use here. So, again, our limits on our t are from negative pi over 2 to pi over 2. Next, we want to go ahead and take the derivatives of all these functions. So dx dt, of course, I guess I switched to t. Let's just use t overall, because that's what I'm going to be using in GeoGebra. It doesn't like me putting in theta. At least it's a little trickier to do that. So derivative for cosine t is negative 4 sine t. Derivative of 4 sine t is 4 cosine t. That means our integral we are going from negative pi over 2 to pi over 2. Our x, we're just replacing x here with our formula in terms of t. So 4 cosine t. Y is replacing with the 4 sine t. That's to the 4th power. And then ds, that's where we introduce our square root of negative 4 sine t squared plus 4 cosine t squared and a dt. Of course, they chose a circle here to make this actually pretty easy for us. This square root, we have sine squared and cosine squared, that makes a 1. What we're left with under there is a 4 squared, but the square root of 4 squared is 4. So this whole square root turns into a 4. Of course, we'd have other 4s. We have a 4 here, we have a 4 from the square root, and we have actually 4 copies of 4. So overall, we have 6 copies of 4. 4 to the 6th power turns out to be 4,096, which we'll just go ahead and pull out of the integral. We have the integral from negative pi over 2 to pi over 2, and we have a sine to the 4th, a cosine, and a dt. And now we just take the integral. Of course, here, the easiest way to tackle this would be to use a substitution. I'm going to let u equal sine of t. That means that du is cosine t dt. So really, we're just taking the integral of u to the 4th and we get to plug in negative pi over 2 to pi over 2 into the sine. Sine of negative pi over 2 is negative 1. Sine of pi over 2 is 1. So this is 1/5 u to the 5th from negative 1 to 1. And that means we get a 1/5 minus a negative 1/5. So we get a 2/5 times 4,096. And that comes out to be 8,192 over 5. Now, we could actually give this an interpretation by going back and looking at our curve here. Or really, we should actually look in 3 dimensions. Go ahead and take that out of there. So we have our semicircle sitting here in 3 dimensions. If we go ahead and plot our function, remember our function there, f of xy is equal to x times y to the 4th. We have this surface here. I'm going to go ahead and actually rescale the vertical so that everything's a little bit more easy to see. Scale this down. Mainly, I want the parts of the semicircle to actually parts of the surface that are above the semicircle to actually be visible. So we have this curve, and we have values of the function over that curve. We can actually even plot that particular curve. So I'm just going to go ahead and take my parameterization for my curves. Remember, that is 4 cosine t. Let me out of there. There we go. 4 sine t. And then before I didn't put in a z value, so it interpreted that as a z value of 0. That's why we're only looking at the semicircle in the xy plane. Now I'm going to go ahead and put my z value, which is the function value at those points. So f of 4 cosine t, 4 sine t. Those are the x and y that are going into my function, and they'll give me my z value. And I'm just going to use the same parameter for my curve. And that will give me this function here, or this curve here, that's really just the points on the surface that are above the semicircle. And what our integral has actually done for us is it's considered this whole thing, everything between the curve on the surface and the curve in the xy plane, and kind of found the area of this piece. We like to kind of think of it maybe as like a fence or something like that, where we found the area of the piece that's between the curve and the surface. And of course, the big value that we got, 8,000 something over 5, is because I've actually scaled the z by so much. It's actually quite a big area over this curve. Now, of course, that interpretation really does require us to be working with something in 2 dimensions. Once we actually start looking at line integrals over curves in 3 dimensions, we're going to lose that interpretation. But at the very least, that's a way of thinking about what the line integral means over a 2-dimensional curve. Let's work problem 9. So here we have a somewhat similar integral, or at least it looks kind of similar at first, but the curve is a little bit different. So here they actually gave us the parameterization. We don't have to derive that for ourselves this time. If we actually want to take a look at it, notice that it is a curve in 3-dimensional space. So if we graph that curve, that is cosine of t, sine of t, t, and then our parameter is t, and we're taking that from 0 to pi over 2. So kind of not a very big curve, you might think, but what this really is, it's a helix. It's spiraling around the z-axis as it goes up. But we've only taken a quarter of a turn, so it only looks like a little turn there. But we're going to integrate the function x squared y over that curve. Now, of course, the first thing that we need to do is take the derivatives. So dx dt, derivative of cosine is negative sine. dy dt, derivative of sine is cosine. And dz dt, well, derivative of t is just 1. We'll go ahead and take our square root right now. It'll save us a little bit of space. Technically here, well, we're taking sine squared plus cosine squared, but then we have to add in a 1 squared, just 1. Sine squared plus cosine squared is 1, plus another 1 is going to give us a 2. Square root of 2. That's going to be our square root. So our integral of x squared y ds is going to be the integral from 0 to pi over 2. That's still the same. X is cosine t. That's squared. Y is sine t. Then we put in our square root, which is the square root of 2. And we have dt. Of course, I'll go ahead and pull out the square root of 2, and we'll make a substitution here. I'm going to make the substitution u equals cosine of t. It means that du is negative sine t dt. So we'll have to deal with that extra negative that will be introduced, but we do have the sine t dt. So we have a negative square root of 2. We have u squared in there, du. Now we need to figure out what happens to the 0 and pi over 2. We plug those into cosine. Cosine of 0 is 1. Cosine of pi over 2 is 0. And this is pretty easy to integrate now. Integral of u squared is 1/3 u cubed. Taking that from 1 to 0. Essentially, the negative here is going to swamp the order here. So we end up getting to just plug in 1. The 0 gives us a 0. But we end up getting a square root 2 over 3. And again, because we're dealing with a curve in 3-dimensional space, there's not really a nice geometrical interpretation for what this means. But you can kind of take the idea that we are taking values of x squared y over this curve and kind of adding them all up. Okay, one more example in this video. We're going to look at problem 10. We're looking at the line integral of y squared z. So a little bit similar to the last one, but a little bit different too. This time the curve that we're going to be integrating over is a line segment. It's a line segment from 312 to 125. We need to come up with a parameterization for this curve. Now, the way I like to do this, I like to think back to chapter 12, where we use vectors to make equations for lines. What we'd like to do is take a vector from 312 to 125. Let's give these names. Maybe I'll call this A and B. So the vector from A to B, I'm going to subtract the values of A from the values on B. So we have 1 minus 3, we have 2 minus 1, and we have 5 minus 2. So we get negative 2, 1, 3. And then we take this vector, we multiply it by a parameter t, and then we add it to our first point. We're essentially going to take r of t to be the vector 3, 1, 2 plus t times this vector here. Or in other words, if we write this out, x, the first coordinate, the first component here, is going to be 3 plus negative 2 times t, so minus 2t. Y is going to be 1 plus 1 times t. And z is going to be 2 plus 3 times t. Of course, our derivative here, because, these constants go away and the t just becomes 1, the derivative of r is really just this vector here. That's part of what it means to be a line, is the tangent vectors are always the same direction. And when we actually take the magnitude of this, remember it's the square root of all these squared, so 4 plus 1 plus 9, we get a square root of 14. But we do, so you kind of can see here that all the derivative stuff can actually be handled by just finding the vector along the line, but we do actually need to know these parametric equations for when we evaluate the integral. So we're taking this, well, I guess I didn't mention here, notice here that when we plug in 0, we get 3, 1, 2, that's A. So A is when we plug in 0. When we plug in 1, we get 3 minus 2 is 1, 1 plus 1 is 2, and 2 plus 3 is 5. So B corresponds to t equals 1. And if you do the same process every time, that's always going to be the case. It'll be from 0 to 1. The y value, that's our function here, 1 plus t. That's going to be squared. Z is 2 plus 3t. We need to multiply in our square root. That's where the square root of 14 comes into play. And we have dt. Next, we have to expand everything out. There's not really any nicer way of tackling this. I'll pull out the square root of 14. But all this expands out to give us 2 plus 7t plus 8t squared plus 3t cubed. And no, I didn't do that in my head. I actually already had it worked out. So you're going to have to be able to do that algebra on your own. When we take the integral, 2 becomes a 2t, 7t becomes a 7 halves t squared, 8t squared is going to be an 8 thirds t cubed, and 3t cubed is going to be 3 quarters t to the 4th. Going from 0 to 1. Again, the 0 here is very nice. Everything becomes a 0, so we end up just getting to plug in 1. That's not always the case. I did have some people on the last exam not actually plug in both limits. They only did the top limit. I'm only able to do that here because the 0 here gives me 0 for every term. Alright, and then we get to add up all those fractions. Again, I'm going to let you do that on your own. I end up getting 107 square root of 14 over 12. So that is essentially adding up the values of the function y squared z over the line segment from A to B, from between these 2 points. All right, so in the next video, we're going to actually look at a different type of line integral that's actually somewhat related to what we're doing here, but a little bit different. So meet me there.